So hi, good afternoon everybody. Thank you for giving us the chance of showing our lab results. So I will change a little bit the topic in the sense that I'm going to talk about clinical applications, and also the size of the devices are going to scale a factor 10 perhaps. So I'm going to talk about position sensitive photosensors, especially those based on silicon PMs. And as I said, our aim is to build arrays of silicon PMs for medical applications. And a particularity of these arrays is that we want to be working inside magnetic fields. The reason for working in magnetic fields is because our current work is to develop PET systems, positron emission tomography systems, which are compatible with magnetic resonance devices. Well, the advantage of these systems, or what one can think about, is that combining these two modalities, the PET, which is a functional imaging technique, with a magnetic resonance imaging technique, is probably very powerful. So only one commercial system is now available, and is based on APDs, avalanche photodiodes. All other systems are based on photomultiplier tubes. So one of the advantages on magnetic resonance to detect the anatomy of the patient is that there is no radiation to the patient, in contrast to CT devices. Our group is, since last year, coordinating an EU grant for studying neurological disorders using multimodal imaging techniques. So we tried to study schizophrenic patients through PET images and magnetic resonance. So the challenge here is to achieve the 1 millimeter PET resolution in reconstruct images when having an insert integrated together with a magnetic resonance image. So the PET system has to be MR compatible. The implications of this system is that one needs a very high intrinsic resolution of the system, high readout capabilities, and also a rather affordable cost, I would say. So this is one of the preliminary sketches of the system. You know that for imaging the brain with magnetic resonance, one needs a dedicated radiofrequency coil. So the idea is that one can upgrade this radiofrequency coil, adding a positron emission tomography system around this radiofrequency. So the distance from the radiofrequency coil to the PET system is about 3 centimeters, which avoids distortions of the big one, the radiofrequency field. So this is the mockup we have built already, and we sent to Karolinska Institute in Stockholm, which is one of our partners. So they are trying to see if patients are comfortable with this insert, because, as I said before, they are schizophrenic patients. So all about positron emission tomography is to detect in coincidence the annihilation photons produced by the positron electron annihilation. So these photons are 511 keV, and usually they are stopped in scintillation crystals, which emit visible light, typically in the 420 nanometers regime, and they are detected with position-sensitive photomultiplier tubes. The problem is that photomultiplier tubes are not MR compatible because they are built with metal. So you know the electrons are going through the cascade, amplifying the signal to be measurable, and this is not compatible with magnetic fields. Another issue that has to be taken into account when designing PET systems to be run inside magnetic resonances is that we have to avoid any type of ferromagnetic material inside the magnetic resonance in order to do not disturb the homogeneity of the main magnetic field. So in this sense, silicon photomultipliers are a good option to build positron emission tomography devices, and many groups, both in the academia and in companies, are researching on this issue. Silicon PMs, as I said before, are avalanche photodiodes that are working in the Geiger mode regime. That means beyond the breakdown voltage. They can be very, very small. They are EMA compatible, most of them, because they can be constructed avoiding nickel, for instance. And the nice thing of silicon PMs is that they achieve an amplification which is as good as for photon multiplier tubes. They are non-sensitive to magnetic fields, as I said, and they are working also at very low voltage, between 20 and 80 volts, depending on the structure of the depletion layer. And they have also good timing properties, which, as I will say at the very end, are very important also for PET systems. So silicon PMs can be fabricated to match very well the emission light of most of the scintillators. LYSO, for instance, is emitting at 420 nanometers, and as in this picture, they can be built in arrays like this one, 12 by 12 silicon PMs, which covers an area of about 5 inches by 5 inches, which is the typical size of photomultiplier tubes. So other arrays configuration like this one can be also achieved. This is from the Irish company SensL, the individual modules. These sensors are from Hamamatsu Photonics, the Japanese company. So in this consortium that I mentioned before, we have SensL, the Irish company. So they are reaching now the level of 100 kilohertz per square millimeter, dark count. So I didn't say before, but one of the drawbacks of silicon PMs is that because of thermal excitation, they have dark noise counts. And they can be suppressed by, for instance, biasing the silicon PMs at very low breakdown voltage or reducing the temperature. So we already test these devices inside a magnetic field, and as you can see in this magnetic resonance image, there is no distortion of the magnetic field. In particular, these devices are what is called through silicon bias. So as a difference from those here, which have a wire connecting the silicon PM to the pads, in this approach, there is a direct connection from the silicon PM through the bias to the contacts. Actually, this is an example of the Hamamatsu very new device. So we test, there are two ways that we are proposing for reading the silicon PM arrays. One is based on application-specific integrated circuits. The other one is based on resistive readouts. So by using ASICs, there are many on the market. One can achieve good performance of the devices. We build our own device in collaboration with another group here in Valencia. Each ASIC can control up to 64 inputs. One can program up to 8 matrices of mathematical combinations, which can provide with the energy of the impact, the centroid, that means the planar impact position, but also the depth of interaction, which is measured through the variance of the light distribution. So this is an example how we program the variance and we obtain information about the photon impact 3D coordinates within the scintillator. So in order to evaluate the performance of this silicon PM ASIC assemble, so we typically use crystal arrays, in this case 2 by 2 millimeters. We scan the bias voltage from the breakdown voltage above something like 5-6 volts, and we observe how the energy resolution improves with the bias. At 30 volts we obtain the best result. It is, as I said before, if you decrease the temperature of the device, you can obtain also an improved energy resolution, here achieving the 7.5% for LYSO crystals. So the temperature also shows that the signal to noise ratio improves. So this is a projection of one of the rows of pixels. In this experiment, what we did is to vary the number of silicon PMs that are considered in the reconstruction of the image. So here 12 by 12, 10, 8 or 6. And what is shown is that because the ASIC integrates all the information of all the silicon PMs. When we decrease the number of silicon PMs to provide the impact position, a better signal-to-noise ratio is observed. So here the signal-to-noise ratio is worse and becomes better as the number of silicon PMs is reduced independently of the size of the pixel. So nevertheless, if one wants to achieve the 1.5 millimeters intrinsic spatial resolution for the entire area, one realizes that using these ASICs, in particular these ASICs, is not possible. So another readout we are proposing is a readout that provides information on each row and column of the silicon PM. So that means 24 signals for this matrix. So and you see the improvement in the signal-to-noise ratio is very significant. So we went beyond measuring a single layer of crystals, and we mount in a stack, so a stagger, 3 layers. So this one is shift in the axial direction, and that one is shift in the lateral direction. And as you can see in this 2D plot, all the pixels of the 3 layers can be distinguishable. That means that the intrinsic resolution of the detector can be below 0.7 millimeters. So here comes the question whether one wants to use pixelated crystal, which is a good solution, but very expensive, or the monolithic approach. So crystals also can be used as a single slab. And this is our current research, to use single slabs of monolithic crystals through silicon PM arrays to provide high resolution on the impact position. So what we are doing is to using the advantage of the row and column readout to observe the light distribution. In contrast to pixelated crystals where all the light distribution happens in one pixel, in the monolithic approach, you have a light distribution inside the volume of the scintillator. You see different impacts. So the same XY impact but different depth of interaction. You have wider if the impact happens very on the top, or narrower if it happens close to the photosensor. So the idea here is to fit the light distribution, and this is what we have been doing the last months. So the light distribution follows the inverse square law. So you see here is simply applying center of gravity to one collimated source, whereas by using the fitting, an improved resolution from 2.6 to 1.8 millimeters is possible, but not only in the XY plane, but also in the depth of interaction, one achieves a resolution of only 2 millimeters. Okay, everything has a drawback. In this case, the problem is that the fitting takes time. Currently it's taking something like 20 microseconds, and because of our electronics, that time is only 500 picoseconds, so we still have to reduce the fitting timing cost a factor 40. So, but still, one can see how center of gravity again, so this is a matrix of 9 times 9 point sources, how improves by fitting the light distribution a factor almost 2, so this is full width half of the maximum of these sources with the center of gravity, and this is with the fitting approach. So last but not least is the timing. As I said before, one of the nice things of silicon photomultipliers in contrast to APDs is that they have a good timing resolution. So people has been measured about 100 picoseconds timing resolution for single sensors. In our case, we approach the 700 picoseconds, but for 144 silicon PMs in coincidences with another 144 silicon PMs. So I must say that the best timing resolution was achieved when using the ASICs, in contrast to the spatial resolution, because when using the resistive readout, so the 12 by 12 readout, we achieve a worse timing resolution, but this is because ASICs are very close to the silicon PMs, they are summed together and only one output is coming out, so there is less variation in trace lengths, there is also no crosstalk of signals, and well, this is a good result. So conclusion, I think I've shown you that there are different ways to pack together silicon PMs to provide a array, matching very well the LYSO or other scintillators efficiency emission light. The ASIC, because it's multiplexing the signals and summing all the noise, is probably not in particular this ASIC is not the best choice for aiming high resolution, but the readout. And monolithic crystals can provide as good as spatial resolution as crystal arrays, and they are cost effective. And as I said, the timing is rather good, but still we are aiming for 200 picoseconds. So this is our next goal, is to bring down this timing resolution. So thank you for the attention.